So this discussion of test 1, and through that we can try to learn some discussion. So let's look at the first question. So this is polynomial is px and x to the 4 plus x to the 3 find as many roots as you can. That was the question. So find, yeah, so let me not write all that. We have questions. So what some of you have done is said that any root should divide 1 or something like that. Right? So along those lines, I would like to say that yes, it is true that any integer root, right? Any alpha integer, if it is an integer such that it's a root, so p of alpha is 0. Yeah. So in that case, you can see directly from the equation, then it must divide 1. So let's see. So there is this alpha. All it just means that this is equal to some alpha, which makes okay. If it is an integer, yeah, then you can can anybody just tell me why alpha should divide 1? Some of you have used it in the test. So why alpha divide 1? So alpha is just an integer. It could be negative also. Yeah. Especially those who have used this fact. So that's right. Yeah. But here we are. First check with 1. So what do you mean by check with 1? Hmm? Yes, but why? No, that's the thing. But why? That's what we're trying to prove. Anything common? Anything common for what? Common in what sense? Uh-huh. Okay. Yeah. But you see, like that reasoning may not work for general polynomials, right? I mean, the consequence you're saying is correct, but that reasoning is not correct. Right? Because quadratic is just a very special case. Right? Okay, so let's see then. Okay, so I will come to that, but can we directly, just from this equation, say why alpha should divide? Just from this equation. I mean, because and because alpha divides these things, right? And so alpha should divide this. Yeah, so this is a more elementary reason, right? It's a more, or rather a more general reason, right? Or if someone is not convinced, what they can just say is, well, you take this alpha on this side. This side is divisible by alpha. The left side is divisible by alpha. The right side is the same as the left side, and so it should also be divisible by alpha. That's the simplest reason. Okay, very simple looking reason, but it has. So we'll see. So then this is fine. But also, let us just complete this problem once again. Then I'll come to that. Vaishana is saying for cubics. I think Aparna also had a slightly different reason. He took the product of the roots and said, we will come to that and see, like, do the work and what we need. Maybe for some other question, you had used the product of roots and so on, right? Right. Yeah, yeah, right. So this one, only two of you submitted. So anyways, never mind. It's very good. But then the problem is now, see, alpha divides 1. It means that our only options in integers are plus minus 1. I mean, these are the only candidates, right? And none of them work. One can just check. Right? So if you put 1, then surely it's not 0. If you put minus 1, then you can just check it is not 0. Yeah, but they don't work. Please check this. Okay? I mean, I am expecting that you have spent some time on this paper at least. So it's better if you have done that. But they don't work. But then the main question is, I mean, then why are there no other roots? I mean, are these the only numbers that we know? Why not half? Why not 2 by 3? Why not some strange number, minus 22 by 30? Those are also numbers that all of you know of. I mean, know of means that we have studied them, right? Then, but that theorem doesn't actually work in that case. What you're saying, I mean, still have. I mean, for example, you look at this equation. Can you tell me a root of this? You will see this has some irrational roots. Is that something that you guys have done? It will have some irrational roots, right? You can even get that, but factorizing is not, I mean, there's a formula and whatever, but it has irrational. So why cannot this have irrational roots? Right? I mean, at least those are the numbers that we know of. So why are there no other roots? That is the interesting part of the question. Yep. That's the other part of the question. This is also one part which I wanted you guys to see if you know or discover this constant dividing the constant term, which we'll come to, which has helped us here. But also why, and that's again will be a theorem, rational root theorem. We'll just state it. Very important. Yes. X square. Sorry. Yes, sorry. That's right. Oh, so you know about imaginary number. Then that's very good. That's also important. Yeah. Yeah. Then, okay. This one will have, right. This one you can check will have some irrational. Good. Okay. So since then you know imaginary numbers, then I should just ask why are there no other real roots? But I'm just, when I say any roots, I just mean in the real domain, real setting, not outside that. Yes, but this one will. So never mind. So that's my point is that the things can have strange kinds of roots. Okay? But why are? But now we need to explain why are there no other? I'll just say real roots. This is the second aspect. You have to somehow argue, even if it's not a proof, just somehow argue that it doesn't cut the real line at all. It doesn't become, never becomes zero. We have done, sometimes they have done this kind of reasoning. Something is never zero. Somehow we reason. So see, one thing is clear. One thing is clear that there are no positive roots. No positive number whatsoever, any positive number, half root 2 will not work, right? That should be clear. No, because again, no, that's the point. That is there when you are looking for integer roots, right? But then we come to other kinds of roots. That's what I'm saying here, right? This x square minus x square. This has some other root, right? So you can check that. Yeah, you know how to solve this. So it's, yeah, this is a root. This does not divide one. I mean, it's not an integer, right? So that dividing doesn't make sense. That is not defined, right? So that dividing condition is what I'm trying to say. Is the dividing condition, it only applies. I mean, it works, but more importantly, more generally, it only applies to integer roots, right? After integer roots doesn't even make sense, right? Why are there no other real? So here clearly we can say no positive. Now please try to reason why there are no negative roots. Okay? No positive roots should be clear. It will be a positive quantity if you put x to be positive, the whole expression will be positive. Can you tell why there are no negative roots? Right. Okay. Mm, okay. Mm, right. So see, now your reasoning will work when sort of x is less than minus 1 or something, right? Or let's see, right? Because the effect of x to the power 4 is not more than x cubed. If x is sort of minus half, then that's not true, right? In fact, then it's lesser, right? X to the power 4 becomes lesser. Or, yeah. So what do you take common? Right? Okay. Mm-hmm. 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 No, you have to. This is a very good thing you have done so far. But now, if x is negative, then what happens? Then this is so. I'm just saying x is negative. I'm not writing this. Listen carefully, everyone. So x is positive, it's fine. If x is negative, this is positive, but this is negative. So why should the total thing be positive? No. Is that always correct? Uh, no, that's right. Yes, right. So your reasoning works perfectly when x is less than minus 1. That's I am That's correct, right? Because if x is less than minus 1, then this x square will be a larger positive number than this is, then x is a negative number. If the magnitude wise, x square will become bigger. Then you are done. This is a good way to arrange, and this does this. But so also or x less than. So this also is settled. But just writing it, I mean, if x is half, then what do you do? Minus half, sorry. So there is a tiny place where you have to still, where we have to still answer the question between -1 and 0. Because now, I mean, it still turns out to be positive, obviously, because there is no real roots. But the reason is not correct, right? Because this is actually having less magnitude. This thing is negative. Right? This thing is 1 is saving. So you have to incorporate that 1 in that final reasoning somehow. Yeah. So that's homework. Okay. So all of you try to show that, but it's because so far you've already done something. Now you have to spend some time and think. Or there are other ways. Yes. For -1 is just one number, so that you can just put and check, and that is fine. But then there are between -1 and 0, there are all those infinitely many numbers which you have to find one general or some general reasoning. Okay. Yeah, but there are other ways to think. I mean, this is also a geometric progression. Yeah, but this is a very, that's why I like to discuss this, because this is like a very new thing. I mean, this I would have not thought of this. I think of something else. Okay. So this is very interesting. But in general, you understand, right, that somehow you may have to partition the real numbers. May have to see different patches on the real number where it's obvious. Basically, the point is that it's not about obvious and less obvious. It's about in some patch, some same kind of reasoning works. In some other patch, the same truth or some other reasoning will have to be given. And that you have to spot. That has to come with more intuition practice. Okay? That is, and one will learn to draw graphs and so on. Then, if you've already known that, you can incorporate that also. Good. So basically, we have shown that this is always, or modulo the remaining part, this is always positive. This expression is always positive. It has to be, right? Otherwise, if it's positive sometime, negative sometime, then it has to cut. That's okay. Good. So we learn now. Let us come to this fact. Let me just write the rational root theorem as it, and then we'll see if there is some reasons that work. So let's call this because this is a theorem that is inspired from what we have, this first question, and it's very, very useful. Okay. The rational root theorem. But let's just write it for a cubic, because let's see if some reason can be given. So here is a cubic, general cubic now. Let us write A also. So we have this. So just say this is the polynomial. If alpha is an integer root, then alpha divides t. Yeah. So how do you show this? Let's see. Ishana, you had some reason that you were giving. So can you say for this? I mean, every root does lead to a factor. So that traditional reasoning might also work. Hmm. Okay. Yeah, but the first thing that you have said, that you have to take some factors from D while factorizing. So do you see that that's a little, I mean, that is not completely rigorous, right? I mean, so otherwise, can we show that for any qubit, any root comes from that some factorization method like that? Though to a large extent, what you're saying is correct because of this other fact that Aparna had used in some other problem. That so should I say this or one more? Yeah, if it's A, then it's also fine. But let's for the moment make it a little easier and just now see that if, but this has some problems. This reasoning has problem. But if alpha, if uh, if alpha, whatever, beta, gamma, delta are roots. Now there could be any roots, not integers or anything. This again leads to another very important theorem. At this we know that this factorization is there. Do all of us know this? That if these are roots and they have this factorization. And this is everything. Oh, yeah. Yeah. So all of us know, right, that this root give rise to factors. I mean, that's why this, that's why understanding the function, for understanding the function, this polynomial function, we use algebra, right? It's factorization and so on, because of this basic fact that roots leads to factors. So this is fine. Now you see, I'm not writing it out, but if you multiply this polynomial and expand it, the constant term is going to be alpha, beta, gamma, a negative of that. So this is the product of the roots, right? And now from what we have shown earlier, if there is two polynomials, I mean, this is also a polynomial and this is also a polynomial. If they are equal, then every coefficient should match. That is not a granted thing, right? As a function, every coefficient has to match. We have shown that because if if a polynomial is 0, then every coefficient is 0. Or either ways, now it's okay, second nature to sort of this is equal to this. But again, there are some problems with this. I mean, to just reason from here. Now see, problem is that from here we cannot say that alpha must divide t, because we don't know the nature of beta and gamma. They could be some very strange numbers. This is a good fact, and it could lead to like a false reason to a correct thing, but it's still false. Reasoning is false, right? Because this alpha, we cannot say that the alpha has to divide t. Even if alpha is an integer, you cannot say that alpha divides t from here, because beta and gamma could be some strange things, right? I mean, you could write 1 as 2 times half, right? Times something. Okay. So these are the things. Okay. Even if d is an integer and alpha is an integer, still the other two things would be. But then, I mean, that's the beauty. That's this very beautiful thing about polynomials, that they are not strict. But a priori, we cannot say that, right? But they are not strict. I mean, that's why everything works, and that's why polynomials have so many hidden properties, right? I mean, the key thing that I'm just trying to say is the following. What do I mean by that the roots are not strange? The roots can be strange, but they sort of have to cancel out, and so that everything in the end is good. What do I mean? The main thing is this. Let's just write anything, and this is something that goes on, and is you studied in higher maths also. Is like, see, if you look at this polynomial px, right? These coefficients, you see, these coefficients are all integers. Now, this could have a bad root, right? It could have a bad irrational root, right? But there must be some other irrational root along with it, or some group of irrational roots coming along with that bad root, so that the total sum and product, they kind of combine, they are good numbers, they are integers. Is that point okay? I mean, this is just it's like a motto that is used in several theorems. It's a spirit behind several theorems. That you could have a bad root like 2 minus root 5, but then it must have its partner. I mean, at least that's what we expect. Or it could have a root like this, but then there must be maybe a root like this or something, so that the sum and the product sort of combined is good, right? Because in the end, it has to satisfy this good equation. And we know that this is the product, and we also know that this is the sum. So bad roots occur, but then there's a symmetry between them. Okay, and that is why this beta may be bad, this gamma may be bad, but the product means in the sense that they may be rational, but the product has to come back to your coefficient domain product, and then so the product will be an integer, and you can do this reasoning. But so far we don't know those facts, right? The product will be an integer, and that can get very complicated, right? So that we will come to slowly, sir. But this is the thing about polynomials, that always there is symmetry and there is some, because in the end the things have to be good if the coefficients are good. So there are many mysteries that come from here, which a lot of things I don't know about. This is studied in so-called this field called Galois theory. And this is this symmetry between the polynomials, between the roots of a polynomial, and how complex that symmetry can be. And then they use that to sort of prove things, some very interesting things, which I should not even state now, but soon I will state. They are very interesting. So far. But then coming back to our original question, is still unsolved. So can we just use the simple reasoning that I kind of gave in the beginning of the class, which is also just a natural thing? I mean, the roots have this factorization property. They lead to this factorization, right? But roots are also simply just things that satisfy this equation. So why don't we look at that side of it and try to reason? That's the other side of roots, right? But from here, it is just completely obvious. Alpha has to divide t. B and C are integers. Now that's, again, I have not mentioned. I should mention that. Otherwise, it's not true. Yeah, otherwise, it might not be true. Yeah. You can give the example. B and C are integers. So obviously from here, we have that alpha must divide D. And so, but it can be, so you have to look at the factors of D, and then positive factors, negative factors. So, okay. All right. Now, yeah, so let's not do applications of this. There's some simple applications. We'll put it some other test. Here is a homework. So there were some problems I gave last time also, which is not discussed yet, but we will do them. Here is the interesting question. Okay. So give example. When you try to construct examples, it's really very important. Okay. Give example of polynomial. I mean, at least 3 degree. Don't go below that. Polynomial. Let me just write the polynomial the 3 degree 3. Sorry. What was I trying to say? I just got which alpha so in which alpha does not divide D, but alpha is an integer. Opposite to what we have proved. Obviously, now the polynomial you make cannot have integer coefficients. So I want you to make an example of a polynomial like this. First coefficient has to be integer, otherwise you can just cheat. You can divide the whole polynomial by some, right? But this you can make any rational number. That's up to you. This you can make any rational number, and keep the d has to be an integer because the d we are saying alpha divided d and so on. So give me an example where you have something like this. Okay, these two it's up to you, and it has an integer root. Let me just write that root even so that it's because that's not the point of the problem. Where 2 and so 2 is a root. Okay, 2 is a root, but 2 does not divide d. D is odd basically. Okay, then you would appreciate the point that it really needs all the coefficients to be integers, and that's also needed in the reason. So note is down. Let's see if you can come up with something. So we have an integer root, but that doesn't divide the last. Yeah, and you can do that by playing around with the and not just by simply dividing. For example, I mean, if this was 2 and 2 was an integer root, you could just divide everything by 2. But I'm not allowing you to make this something else other than 1. So, okay, that's all. One of them plus 2, 2 plus 2, 2 is a root. Okay. Fine, it's good. So let us come to one more version of the rational root theorem, which is the same more or less. Something is the same. If 1 by n, now we need a, is a root, n is an integer. N always denotes a integer or natural number. Is a root, then so what do you think I will be writing? Or what's the natural thing that fits here? What divisibility condition should it satisfy? Then n divides no, not 1 by d. I mean, I can, yes. So that is somewhat 1 by d, but it's not 1 by d. Let's a by d. Yeah, let's see. A by d need not be an integer. Right? So it is like that. So let me not say what it is. Let's just write and we'll understand. I mean, if it's a root, then you just, I mean, one way is to just guess, but also you can just write. If you just write, then what do we get? We get this. Now you want to make a divisibility claim. How do you make a divisibility claim? The natural thing is to just cross everything out, cross multiply, and just get. Yes, that's it. So that's, and we are almost also there with the proof also. Just right time, almost. And you can see, so as I say, it's like the same problem. It's just the, yeah. Yes. So it's, you also see something interesting. The coefficients getting swapped in this new polynomial and the root getting reversed in some sense, in one sense, and the coefficients getting reversed in some sense. And this is the thing, it's also a theme that you'll keep seeing all some things. So now it's the same thing, the NF divide. So that's the point. And combined with all this, we say that this trivial p by q is a root, or maybe I should say m by n. I've already used a p. M by n is obviously for all this to work, coefficients need to be integer. Is a root, then m by n is a root, then m must divide t, and n must. I mean, this is just a necessary condition. It's by no means sufficient, and I'm not saying that if some m divides d and n divides a, then it will work. No, that's certainly not true. I mean, otherwise, if whenever the coefficient is 1 must be a root, or minus 1 should be a root, but we've seen it's not. It's a simple theorem. To begin with, it's a simple theorem. There are many variants of this, many interesting variants of this. So if there are any questions, then ask. And you will find plenty of exercises for just if you just Google rational root theorem, maybe AOPS will have a link for this, and you'll find some simple practice problems. Just go and just practice, because there'll be some calculations which is important to do to get more. I given some problems. I'll put some in the test, and I'll just send some other good resource. Challenges and thrills is it's a bit limited in polynomial. It has the, I mean, challenges and thrills is best for geometry. You see the geometry section, right? It has just the best. It has so much nice geometry, but others it is lacking. Yeah. And mathematical circles, I don't know if they do much polynomial. So anyways, this is just the standard names. Okay. So we have done this case. Yeah. So what I was just going to say is this is if you put all this into this way, you can see it's a very interesting way to say all this. Basically, we're saying that if you have this kind of polynomial, monic polynomial, right? Then so I mean, you're looking at integers, yeah. And if you go to the next thing to them is q, right? In what sense it's the next thing? I mean, it just provides an inverse for every element, right? 2 inverse is half, means the multiplicative, right? So I mean, that's the thing about q. It just provides the inverse to every, right? Now what we have proved so far is that if this has a rational root, yeah, if this has a root which is a rational, then it must be an integer. Do you guys agree? If this has a rational root m by n, then it must be, because n has to be 1 because the leading coefficient is 1. If you're looking for roots in q, then they are actually in Z. Provided you're looking for them in Q. If you're looking for them outside Q, then I don't. There are obviously roots outside Q. But if you're looking for them inside Q, then actually you have to jump down to Z. And again, this is the feature we'll see. This is called integrally closed. Okay? So Z is integrally closed, meaning that if you're looking for a root, if you write a polynomial which has coefficients in Z, and if you're looking for roots of that in just the next thing, then you'll actually find them there only. So it is closed in that sense, it's sufficient, it's closed in, right? In that sense, called integrally. Integrally because this is integers. That's some of the reason. Okay. So far, this is what we have done. It's a very important step. Maybe I can give one more exercise. Try. So we said that if okay, we said that if m is a root, then m divides d. If m is an integer root, then m divides d. So m is p of m 0, we said that m must divide t. But now what I'm also saying is m square must divide cm plus d. So m divides d is what you have already proved, but this should also be true. And also m cube should divide bm square plus cm plus d. So you can quickly eliminate roots, whether something is a root or not. Uh, uh, you can also make the small checks before actually putting them in the entire polynomial and checking, and seeing most often that they don't work, that they are not actually roots. I mean, right? You take the factors and they are the candidates, but then you can quickly eliminate them by making small checks. But first, you prove this result. This I think is correct, hopefully, and you can check it. Right. It's not just true that m must divide d, but m square must in fact. I mean, you can just prove in fact m. I'm okay with that, but it's the same. Right? See, I mean, I'll just take some example in fact. That m square or m should divide cm plus d. It's easy. It's almost there. So these are the things that we are doing, right? Rational root theorem. Okay. So then let's you can note this. Hopefully, this is I will be doing this next time. So don't just right. Yes, that's right. That's right. Yeah, but then yeah, so that's why maybe m square is better. M square divides cm plus. Yeah. Yes, I missed that thing. What you said is correct. That m divides cm plus d is very easy. Yeah, but m square must divide cm plus d, and m cube must divide bm square plus cm plus d. And it also goes on if it's a higher. Good. Right. All these small kind of optimizations used, especially when one is trying to just put this into some system which does the calculations, then this is useful. Otherwise, these are not very useful. Theoretically, these are not very useful. For us, it's just everything is good as long as it is a good problem to try. Now let's move to the next one. Find at least one root. So this one I think was done. Ishana. One I don't remember. That was sent it long time back. So, x square plus x. Why is the laptop is heating up? I just replace the fan sometimes back, and then just after 1 month, again the fan is. Again it gives me a message all the fan is not. Money is gone to this thing. So again, we want to just find at least one. So I mean, it's easy to check that 1 and -1 are roots. And again, it's easy to check, it's easy to guess, and easy to check, right? And then from here, I mean, that was the question, right? There was nothing else asked. We did not ask to find all roots or say if there are no other roots, but no problem. Done that, that's even better. So this one is easy. This one is, I mean, these are the reason why I am, no, so 1 is not a root, right? -1 is a root. Right? Yeah. -1 is. Okay. Does anyone have any other reason why -1 is a root apart from just putting it and checking it? Any other interesting reason? There is an interesting reason. It's not just a coincidence. You can understand, right? The odd, starting from an odd, this thing, x to the power 11 to x to the power 10, it will also again -1 will be a root. Does it mean anything? Yes, that's right. That is essentially that's all it is mostly. Yeah, that is mostly all it is. Yeah. So then let's yeah. Okay. I mean there is a job. Uh-huh. Yeah. You mean an odd degree polynomial will cross the x-axis? Yes, that's right, and that's the. But yeah, but here we already find one root explicitly, and it's asked to find the root explicitly. So just knowing that it crosses is not enough. Right? But interestingly, it crosses the x-axis only once. That is interesting. Right? Only once it crosses. That also you can try to. It only crosses the x-axis that minus. How you prove it? So why no other root there? And so my point being that in general, when you write this equation, it will either have one root or no root. If n is odd, then there is one root minus one. If n is even, then there are no roots, and that is the story about this polynomial. Such a huge polynomial, but it only has one real root. No other like irrational, blah blah blah, nothing works. No real number works apart from minus one if n is odd. Why that is the case? Why this has no real? So because for small powers you can give some ad hoc reason, you can give some reason. But let's just say that you have x to the 10, to the 9, to the 8. Why does this not have any real root? Why? So this was the first question, was also this, but we use some other reason. Now let's come to the other, and some small part was left, I think. But let's use some other reason here and see. Anyone else? Anything? Maybe you guys don't have. So no problem. The point is that this is a geometric progression, and you may know how to work with the geometric progression. Even if you don't know, here is the trick. Then it's just a trick. Otherwise, it's a good way to see. But let's just see it as a trick. No problem. If you multiply by x minus 1, can you tell me what the left-hand side becomes? This is a dot dot dots. Okay, so x is. What does the left-hand side become? That's true, but does it become anything special? Yeah, x. That's right. Everything else cancels out. Not a surprise. You can see that it's worked out. Huge thing, but everything cancels out. You can see, right? X times x to the 9 is x to the 10, but then there's a minus x to the 10. Similarly, x times x to the 8 to the 9, but then x to the 9 times minus 1 cancels. Right? This is the thing. This gives, so you see this as a function, it's fine, but as a polynomial, when you multiply it by x minus 1, you get a higher degree polynomial, but it is better understood. And all understanding of that x to the 10, x plus that can be gotten from the x to the 11 minus 1. Now it's a more easy homework maybe to show that there are that what are the, I mean, how many real roots can this have? Certainly one is there because we have already, yeah. Can this have any other real roots? Okay, and that's not even a homework, right? Because it's very easy. Because x to the power 11 minus 1, if you want roots, you do this. But I mean, that means this. So, but that all we know this, that I mean, x has to be equal to 1. Among the real numbers, there is no other number, right? That when raised to 11 power can give you 1. Right? But then, so what do we learn from here about the previous, about the original polynomial that we started? What can we say? can we now say that it had no real roots? So go back and see from the question, what was the initial question? Why no real roots? Then we changed the polynomial in a specific way. Just multiplied a factor. The resulting polynomial has only one real root. That's right. Right. See, x minus 1 is 0. What does that mean? X minus what I'm saying is, just saying x minus 1 is 0 is not a, x minus 1 is 0 for x equal to 1, right? So maybe, yeah, basically the problem comes from here. What I've written, I should say that if alpha satisfies this, then alpha has to be 1, right? But not to be confused, right? This 1 is the, but that doesn't mean that this x minus 1 is 0. No, I mean, that is just a polynomial. It is not 0, not a 0 polynomial. For x equal, when you put x equal to 1, then it becomes. Just let me know if there is any confusion. Yes, yeah. I mean, okay, not this one, not that px, this one. We want to tell that this has no real. We only added a factor and we saw that there is only one root. That root belongs to that factor. I mean, that one is the only possibility, right? That's what we have seen. But one doesn't satisfy this thing. One doesn't make the 0. There is no root. Right? See, when you come down from here to here, you don't lose any roots, right? I mean, if something made this 0, it would also make this 0. Right? That was how it is defined. Right? The product of that and something else. Is that point? Yeah. Just think in terms of like numbers, right? So when you put a number, right, and this becomes 0, but then that number better make this 0 as well, right? Because that's what you're doing. These are the same things, right? I mean, so what I'm trying to say is, just another way to say it is, see, when we say that this happens, when we say this, what do we mean? Obviously, we need to multiply to check it's correct. But it's also true, and all this is also true, that for every number, this is satisfied. Right? That's what it is. That's how the multiplication is on polynomial is defined, right? That for every number, this must be true. Right? So if there is some number for which this becomes 0, like this becomes 0, then this becomes 0, so this becomes 0. But as easy as that may sound, this means that alpha is only 1. Suddenly, something which was completely not clear, that there is any other root or not, when you give it a factor, when you give it its missing piece, then somehow it becomes very easy to say. So, so there are no roots because one is the only possibility and one doesn't work. Yes. Is it fine with everyone? So that's okay. So let us keep it to this today. Let's keep it a little because I think we did a new thing. So I want you guys to now just maybe after the class 10 minutes on this, think about what we did. Just go over it. Okay? Go over it a little bit and try to. Because you don't want to cram too many things. It has to be useful. So just wanted to check just because this topic, this rational root theorem is very regular topic. I just want to see if I can give some problems directly from here on, from somewhere on the internet. Brilliant. Yeah. Brilliant has some very easy, not easiness, has a very organized way, very nice, wonderful place. Right? So you can see this is a theorem. You can should read all this if you want, but just you see factorize this. Finding roots by using this is something practice that you should just do. But now I'm telling you, like as an official should do. Yeah. And you see this. This you can also read some examples if you want. But my main focus would be that problems. These problems, at least, you should definitely do, and just do this as much as you get, many as you can. These are some of them later ones might be harder, but just try. Please do this. Do not do this. Write it, and maybe it won't send it. Okay. All right. So, I mean, did you guys see the screen? Was it visible? Yes, it was. It. Okay. Good. Yes. So then that's it, right? Yeah.